Okay, let's play a game. I have 2 cups here. I also have 2 measuring spoons. One is a teaspoon and the other is a half a teaspoon. You can't see which spoon is which, and I'm going to use one of the measuring spoons to fill up 1 cup with water and the other to fill up the other cup in consecutive terms. After each turn, I want you to figure out which cup is being filled up by which spoon. Got it? But there's a catch. Each time before I add a unit of water to each cup, I'm also going to add half a tablespoon of water to the cups. Actually, sometimes I'll add half a tablespoon, sometimes I will add 4 half a tablespoons, sometimes 2, and sometimes 0. Let's do an example. For turn 1, here's half a tablespoon added to 1 cup along with the water from one of the mystery spoons. For cup 2, I've added 2 half tablespoons and the water from mystery spoon 2. Which spoon is filling up which cup? Do you know? How many turns would it take you to figure it out? And the answer to this question is related to why this stacked image of Messier 101 looks worse than this image, even though both have the same amount of total integration time, both were shot with the same scope on the same nights with the same camera. The answer to this question is also why you can use histograms to help judge whether your astrophotography sub-exposures are long enough. Let's talk about it. Welcome to Deep Sky Detail. I've seen a few comments on forums and videos that claim that with modern CMOS cameras, it's okay if the histogram is clipped on the left edge because you can still get a good photo. Comments sometimes might say that you can use the histogram to tell if you're clipping the stars, but for fainter signal, it doesn't matter. In other words, the histogram doesn't know how faint the object is. While I 100% agree that you can still get a good photo with short exposures, I disagree that it's a good idea for the histogram to be clipped in terms of SNR and efficiency, especially if you have very little light pollution and are imaging with a slow telescope like an f9 or an f10. The histogram might not know how faint the object is. The histogram isn't intelligent. It's just a measurement tool. But it does contain information, and interpreting the left side correctly is trickier than interpreting the right side, but it's still important. Let's look at these stacked images of Messier 101 and their histograms. This image used 15-second subframes, and this one used 120-second subframes. These are stacked images. They've been calibrated with darks, flats, and dark flats. The histogram represents the average of many stacked subframes. If we look at the histograms of both images, both of them are clearly fully away from the edge. You may be tempted to say, well, the final stack's histograms look good, so what if the histogram subframes are on the edge? It shouldn't matter. Well, to me, it's clear that the stack of 15-second subs is much worse than the stack of 120-second subframes. Critically though, if I imaged Messier 101 about 4 times longer with 15-second subs, it would look about as good as this stack of 120-second subframes. I can still get a good image with 15-second subframes, but it will take me about 4 times as long. Now let's take a look at the subframe histograms themselves. These subframes are calibrated, meaning they have had darks subtracted and they've been flat corrected. The 15-second subframe obviously looks worse than the 120-second subframe. So let's look at the histograms. The histogram of the 15-second calibrated subframe is right against the left edge. The histogram of the 120-second calibrated subframe is not. The histogram is telling us that we are clipped with the 15-second sub. This isn't a coincidence. But why? Why isn't it a coincidence? Shouldn't the histogram of the final stacked image be the only thing that matters? Why does the subframes histogram matter? And why am I using calibrated subframes? Am I tricking you somehow? Each cup had water coming from 2 sources, 2 mystery spoons and a half a tablespoon. If water weren't coming from the tablespoon, then we could very easily figure out which mystery spoon was bigger. But because of the uncertainty of adding water randomly from the tablespoons, our observations become less reliable. Eventually, I'll be able to figure it out, but it's going to take a long time. You probably already know where I'm going with this. The tablespoon represents the read noise of the camera. The cups are 2 different pixels. Each time you take a subframe, you add a little bit of uncertainty to your image's measurement of light that comes from the sky. That's the tablespoon of water. On very short exposures, your light measurement is tiny, and the read noise can overwhelm that measurement. If you take longer exposures, suddenly your measurement of light coming on each subframe becomes larger. The read noise is swamped by the signal. If our goal is to distinguish the brightness between 2 pixels, so to know which cup gets more water, then if your subframes are too short, you may need 2 or 4 or 25 times more integration time to get an image of similar quality as an image with slightly longer subframes. So I showed you what a calibrated subframe's histogram looks like. If you are not using a 16-bit camera, or you're using a large offset value, you're going to need to interpret the left side of the histogram a little bit more cautiously if it's uncalibrated. But it's not hard. That being said, the histogram of a subframe shows you the brightness values on the x-axis, usually converted to 16-bit ADU, and the number of pixels that have those values on the y-axis, sometimes just called the count. Histograms usually group similar pixel values together in a bar. So pixels that have 1 to 10 ADU are grouped together, 11 to 20 ADU are in the next group, etc. Your camera is going to pick up on several sources of light or things imitating light during a subframe. The first level is the read noise plus the dark current plus the offset. Every time your camera takes a picture, it adds fake photons randomly to each pixel, even if no light enters your objective lens or mirror. This is just a limitation of the technology, and there's not really much you can do to change that. So this is added with the dark current, which is much less random, but still random. The offset, on the other hand, adds a constant value to each pixel. It is not random, but it can make the histogram artificially become separated from the edge. Offsets are needed for dark frame calibration. If the offset is small, the resulting histogram will be right up against the left edge of the histogram. If you have a 12 or 14-bit camera, then the offset can drastically move the histogram to the right even with a small offset. Top of the read noise is the sky glow. This includes light scattering from stars, including, believe it or not, our sun, as well as light pollution. Even in Bortle 1 zones, you have sky glow. In those areas, sky glow is caused by light from stars and ionization of gases in the upper atmosphere. If you are in dark skies during Milky Way season, especially in the southern hemisphere, the Milky Way can cast a shadow that you, with dark adapted vision, can probably see. That's part of the sky glow. This sky glow adds brightness to each pixel, moving the histogram to the right. You then add on top of that the light from the deep sky object you're imaging. And the associated noise from sky glow and the deep sky object is gathered when the shutter is open. So for those sources, it doesn't matter how long your subframe is. But the read noise depends on how many subframes are in your stack. If the read noise is the biggest source of noise in your subframes, your subs are too short. The trick is to learn how to read your histogram. This method works best for modern CMOS cameras because the read noise of CMOS cameras nowadays is so low. If you have an older CCD camera or CMOS camera with higher read noise, this method will still work, but you may want to make sure there is even more of a gap between the dark histogram and the light histogram. The idea is simple. We want to know whether the signal in our light frames is strong enough to rise above the camera's read noise. If it isn't, then each subframe is dominated by read noise, and stacking becomes very inefficient. One way to check this is to compare two things: what the camera produces with no light, so just the read noise and the offset, and what it produces during a real exposure. If these two distributions overlap heavily, read noise is still a big part of your image. If they're clearly separated, then sky signal is dominating, which is exactly where we want it to be. So first, take a bias frame or a short dark frame. Either one should work with modern CMOS cameras. The exact time doesn't matter, just as long as it has the same gain and offset settings that you will image your light frames with. The exact time doesn't matter too much, but most likely any time lower than 2 minutes should work. Then put it into a program that can zoom into the histogram. ASI Fits View by ZWO is actually pretty good, although the y-axis isn't linear from what I can tell, which results in exaggerated tails, and it can make you think that the read noise is bigger than it really is. So here is a bias frame from my target of Messier 101 with the same gain and offset settings as my M101 image. I'll go ahead and right-click and select Histogram, then press the Zoom button. The bulk of the histogram, minus the tails, sits around 3200 ADU, with most of the values spread out between 3150 and 3240. That spread is proportional to the read noise of the camera at these gain settings. You can use the center slider to figure out exactly where the bulky part of the histogram ends, and with ASI Fits View, the tails are exaggerated. Because my camera is a 14-bit camera and I am using a gain of 50, 1 ADU here does not represent 1 photoelectron. But now we can compare that to a 15-second light frame. The bulk of its histogram starts at 3167 ADU, which overlaps pretty heavily with the bias frame distribution. That tells us the signal from the sky hasn't pushed the data far enough away from the read noise yet. In other words, the read noise is still a significant part of the signal. Each time we stack another image on top, we're adding about just as much read noise as other types of noise. It's really inefficient. So now let's look at the 120-second subframe. The left part of the histogram starts around 3360, and 3360 is above 3240 by more than 100 ADU, which I think at this gain setting is probably about 30 extra photons per pixel. That gap means the sky signal has lifted the data well above the read noise floor. That's exactly what we want. So the goal isn't to push the histogram to some magic percentage across the graph. The goal is simply to move the light frame histogram far enough away from the camera's own noise distribution. You can do this with almost any software that lets you zoom into the histogram and read things in the raw ADU. I used ASI Fits View here because it makes it easy to inspect the exact ADU values, even though its y-axis exaggerates the tails a bit. The specific program doesn't matter. What matters is being able to compare a bias or dark frame histogram against a light frame histogram taken with the same settings. Now, I'm going to plot all of these images in statistical software with a linear y-axis. Here's the histogram for the dark frame. Now here's the histogram of the 15-second light frame. Notice that there's overlap between the two histograms. That's not good. Here is the histogram of the 120-second light frame. See this gap? That's a lot better. So why does this histogram trick work? Well, it all has to do with noise. Remember earlier in the video I said, even in Bortle 1 zones, you have sky glow. In those areas, sky glow is caused by light from stars and ionization of gases in the upper atmosphere. If you are in dark skies during Milky Way season, especially in the southern hemisphere, the Milky Way can cast a shadow that you, with dark adapted vision, can probably see. That's part of the sky glow. This sky glow adds brightness to each pixel, moving the histogram to the right. You then add on top of that the light from the deep sky object you're imaging, and the associated noise from sky glow and the deep sky object is gathered when the shutter is open. So for those sources, it doesn't matter how long your subframe is. But the read noise depends on how many subframes are in your stack. If the read noise is the biggest source of noise in your subframes, your subs are too short. Once the histogram has moved far enough to the right, the shot noise from the sky glow dominates the total noise. Shot noise depends on the total amount of light collected, the total integration time, regardless of how that time is divided. But read noise is added every time you take a sub-exposure. So too many short subs means we're accumulating read noise which we can avoid. So once we're in a mode where the sky glow noise dominates the total noise, we don't need to go any longer. We want our exposures to be sky limited, not read noise limited. So why is there so much confusion on the internet? I'm not 100% sure, but there are two plausible reasons that make sense to me. First, histograms, especially in software used for image acquisition, don't zoom in enough, and the y-axes of the histograms are on a logarithmic scale. You can't actually see where the left edge is, and the y-axis makes it look like the histogram is always on the left edge. The second is that histograms, especially in image acquisition software, don't show you where 0 ADU is on the x-axis. This is the K-stars histogram. The mean of the histogram for this dark frame is about 3200, but the histogram says the intensity starts at 0. The x-axis is wrong. The software is making assumptions about where the left edge of the histogram should start, even with longer exposure light frames, and I've checked, zooming into the histogram always has this problem, where the histogram looks like it is on the left edge. I think this is misleading and makes it more difficult to tell what a good sub-exposure time is. The takeaway is simple. Your sub-exposure should be long enough that the sky noise dominates over the read noise. Let's review. If the calibrated subframe histogram piles up against the left edge, read noise is likely dominating your subs, and they're too short. You can compare a bias or dark histogram to a light frame if you don't want to use calibrated subframes. If the light histogram clearly sits to the right with minimal overlap, you're likely sky limited, which is good. And 3, modern CMOS cameras have low read noise nowadays, so the required sub lengths are shorter than they used to be, but it's still not 0. And then 4, the optimal sub exposure depends on a sky brightness, filter, and target, not just your camera specs. And here's one last tip. If you really need shorter exposures, for example with lucky imaging or poor tracking, or if you're prioritizing sharpness, you can sometimes compensate by increasing the gain. On most modern cameras, higher gain reduces the effect of read noise. That means each short exposure is less dominated by read noise, even though you're collecting less signal per frame. There is a trade-off though. Higher gain also reduces dynamic range and full well capacity, so bright stars will saturate sooner. Even though the images may look noisier on the screen, that's mostly because both the signal and the shot noise are being amplified. It isn't creating new photon noise, it's just changing the balance between read noise signal and dynamic range. In situations where you're forced to use shorter subs, it can make stacking much more efficient. If you enjoyed this video, consider subscribing, liking, or becoming a channel or buy me a coffee member. I did a series of experiments with broadband and narrowband looking at sub-exposure length. The first video in this playlist examines the data I showed in this video and even has statistics. Or if you would like to know why light pollution is way worse than read noise ever will be, consider this video. Thanks for watching.